Here's the same AI model answering the exact same question. Watch the speed difference. Same model, same output, same quality, but one is 7.4 times faster. The secret is a simple caching trick that every modern AI uses. Let's see how KV cache works. First, let's understand the problem. AI models generate text one token at a time. Here's what happens. Each new token must attend to every single previous token. Token 3 attends to 2 previous tokens. Token 10 needs 10 computations. Token 1000 needs 1000 computations. This means quadratic growth, and A is big O of n squared. Result: generation slows down with every new token. Here's the solution. Let's look at the attention equation. Attention equals softmax of Q times K transpose, all multiplied by V. We compute 3 matrices: queries, what we're looking for; keys, what we search through; values, the actual content. When generating token n plus 1, the keys and values for tokens 1 through n haven't changed. They're exactly the same as before. If we were to generate token 5 using the old way, we need to recalculate K1, K2, K3, K4, along with V1, V2, V3, and V4, and calculate Q5. But using KV cache, we store K1 through K4 once, store V1 through V4 once, and reuse the cached K and V values to calculate Q5. This drops our complexity from n squared down to n. Instead of recomputing everything, we only compute what's new. Let's see this in detail. Here's how attention works with 4 tokens. The quick brown fox. Each cell shows how much one token attends to another. Notice the causal mask. Tokens can only attend to previous tokens, not future ones. When we generate token 4, we need to compute attention across all previous tokens. That's the expensive part. But here's what KV cache realizes. We already computed the keys and values for tokens 1, 2, and 3. Why throw them away? Let's walk through a concrete example. We start with once upon A. Step 1, we compute keys and values for all 3 tokens, but instead of discarding them, we store them in our cache. Step 2, now we generate time. We only compute 3 things: the query for time plus its key and value. That's it. We append the new key and value to our cache and use the query against all cached keys and values. Notice what happened. We went from recomputing everything to computing just the new token's representations. The cache grows linearly with each token. The formula: sequence length times layers times heads times dimension times 2. For a 7B model, that's about 1 megabytes per token. In practice, KV caching provides 3 to 5 times speedup for typical generations, and up to 10 times for very long sequences. Let's see how this actually works in code. Here's a simple PyTorch implementation of a KV cache. First, we pre-allocate memory for our cache, separate tensors for keys and values. Notice we allocate space for the maximum sequence length up front. The magic happens in the update method. We simply append new key value pairs to our existing cache and return the full cached sequences. No complex logic, no recomputation, just smart memory management. The cache grows incrementally with each new token. This same pattern is used in production frameworks like transformers and vLLM, just with more optimizations for batching and memory efficiency. This optimization is why ChatGPT responds in real time, why Copilot suggests code instantly, and why we can run powerful models on consumer GPUs. Modern frameworks handle this automatically. In Hugging Face transformers, just set useCache equals true. In vLLM, it's enabled by default. Here's what this means. A 13B model generating 100 tokens might take 30 seconds without caching, but only 6 seconds with it. But there's no free lunch. Let's talk about the memory cost. A 70 billion model with 8K context needs 35 gigabytes just for the cache. The formula is unforgiving. 2 times batch size, times layers, times heads, times sequence length, times dimension, times bytes per parameter. For long conversations, this can consume gigabytes of memory. That's the trade-off, memory for speed. But researchers developed several optimizations to address this. Multi-query attention shares keys and values across attention heads, reducing cache by 8 times or more. Grouped query attention offers a middle ground, sharing across groups of heads for 4 times reduction. PagedAttention manages cache memory like an operating system, swapping chunks in and out. Note that KV cache only helps during inference when you're generating tokens one at a time. Training still needs full attention computation. If you found this useful, please subscribe.